Hi, I am Samuel Fonseca and I and Felipe Duan will present this paper. So this is a collaboration work with researchers from three different universities, including Federal University of Roraima, Federal University of Amazonas and Durham University. The paper is about automatic contextualization of program assignment lists using natural language processing and machine learning. Introductory programming classes, often known as CS1, are nowadays often compulsory for undergraduate courses that do not have computer as the major. For example, mechanical engineering, economics, etc. In this sense, there are students with difficulty interpret assignment text due to the lack of affinity with the area of the problem. As a result, many of these students may be discouraged in CS1 as they fail to see the purpose that programming can have in their professional lives. It is a common sense that we learn programming by doing. That is, students need to solve many problems to improve their skills. And here the online judge comes in. Online judge automatically assesses the student's code and give the instantaneous feedback whether the code is correct or not. These systems also decrease instructors' workload by automatically correcting the student's solutions. Moreover, online judges have a large number of problems in the problem banks, so there would be plenty of problems to select from for both students and teachers, allowing for a mass personalization, where a teacher could meet the needs of many students in parallel. However, the problems available in these systems are often collected or scrapped from various environments that do not provide labeling, and thus it is laborious to find appropriate problems for non-CS students. Notice that contextualized assignment lists with programming problems related to the student's major could enhance engagement in the learning process. To illustrate, undergraduate students of economics would be more familiar with an if and then also problem, using terms such as interest rates or importation of goods instead of a problem on the growth itself, which may be completely out of the comfort zone. However, preparing these contextually personalized program assignments for classes for different courses is really laborious and would increase considerably the instructor's workload. And it gets harder as the number of program exercises is constantly increasing. Therefore, the automatization of the categorization of the problems based on subject matter is becoming vital to support instructors to create contextualized assignment lists for different majors. So thank you so much. From here, Felipe Duan will present the paper.
In this sense, we raised the following research question. How can we extract the subject matter from programming problem statements to automatically match programming assignment lists to non-CS courses? To respond to the research question, we propose a new holistic methodology pipeline for online judges' contextual labeling problem. Moreover, we extract for the first time to the best of our knowledge automatically and precisely subject matter related to non-CS courses. And we propose a subject-based contextualization taxonomy to map subject matters to non-CS courses where CS1 is compulsory. As an instrument, we use the Codes Bench Align Judge, which is self-designed platform on which instructors can create program assignments, check students' progress, etc. For the student side, they can solve the problems on the embedded IDE and get back instantaneous feedback whether the solution is correct or not. Here is an example of the CodeBench interface. We analyze, in terms of methodology, we analyze CS1 courses delivered to 15 non-CS undergraduate degrees from the Federal University of Amazonas. These courses are divided into 5 major areas, including mathematics, physics, engineering, statistics, and geology. During the courses, students solved 7 assignment lists of different programming topics and increasing difficulty. Students used the Python programming language to solve the problems. Note that despite the problem lists are well structured based on these programming topics, they lack a clear division based on the contexts in which the problems are to be delivered to related major areas. The database in our online judges system consists of 986 programming problems in the CS1 discipline. The statements in the database were initially not categorized by context. Thus, we proceeded to create a labeled corpus by manually classifying the context of each statement to further use to carry out the experiments. And as labels, we adapted for our research context extracted from Zanini and Hab's definition, which show that the context of problems plays an important role for novice programming students. As a result, we produce a total of 23 contexts, which we group together in a new CS1 context taxonomy, which maps the non-CS undergraduate courses that may have a high connection with each of these 23 contexts aforementioned. And it's worth noting that we perform a statistic test that measure inter-annotator agreement to validate if your annotation process was conducted properly. To do so, we used coherence kappa, which showed the level of agreement between two annotators in a classification task. And as a result, you achieve a key equal to 0.96, which is considered almost perfect agreement. And this is our proposed automatic contextualization research methodology pipeline. We create here a pipeline studying various combinations of the most popular and successful blended state-of-the-art techniques for natural language processing. The data augmentation stage consists of balancing the training data by paraphrasing it using the pre-trained model BERT. In this work, experiments were carried out with and without paraphrasing, this contextual paraphrasing, in order to analyze how the balance by paraphrasing can influence the results. For a second phase, as all our problem statements were originally in Portuguese language, we opted to translate our statement to English, as there are many tools available for processing text written in English. Subsequently, we proceeded in applying our pipeline with and without the use of step words removal and lemmatization. As a result, we observed empirically that these two techniques were useful for data filtering in our pre-process step, so we opted to use them. For the third phase, it's worth noting that the machine learning algorithms take as input a sequence of text to learn the structure of text, just like a human does. However, we need to convert the data in numerical form. As such, we represent our text data as a sequence of numbers. In addition, the ML algorithms expect each training instance to have the same length, same number of tokens. Thus, we paired with zeros at the end sequence that are shorter than the maximal length sequence. In addition, two different state-of-the-art NLP techniques for vector representation of words are used for competing against each other: Google News Vector and Blue Word Embeddings. Moreover, for the BERT classifier, we use its own layer of word embeddings, similar for the other deep learning models. For the fourth phase, we created a process to obtain the best model for automatic categorization of contexts of programming questions. The process allowed us thus to carry out experiments with deep learning methods and to compare not only those approaches with each other, but also with classical approaches such as shallow learning models, as can be seen in classifier step. Finally, to validate the model, we employ the stratified validation with tenfolds. It should be taken in consideration that we perform the data augmentation only on the training sets of each training fold. Thus, there was no paraphrasing text in the test sets. As a result, we built a total of 34 predictive models. This figure illustrates all the results obtained by all models applied to this research. From visual inspection, we can notice that paraphrasing improved the F1 score in all models. Indeed, we confirm statistical significance after McNamar's hypothetical statistical test, even after Bonferroni correction. Moreover, the best model found is the Birch classifier with the use of contextual paraphrasing, with the highest median and low standard deviation achieving an F1 score of about 95%. Again, we validate this affirmation by using McNamar's statistical test. Here, in this figure, you show the performance of this model for our best model for each context as a heat map plot, where the rows represent the actual values, while the columns depict the predicted context. In general, our best model is capable of recognizing problems from each context with a high recall. Indeed, there are predictions in some classes without misclassification, such as computational, sports, etc. However, we can see some minor errors which can be justified. It turns out that statements might have multi-contextualization, that is, a statement can address more than one context. However, what happened is, in practice, is that one context is predominant, and the prediction of our model reflects this. So, as a conclusion, our best model, which is based on the Birch technique with paraphrased balancing, was able to achieve a performance with high precision and high recognition rate for all 23 class statements. Indeed, we achieved an F1 score of 95% with a minimal error rate. We believe that the automatization of the classification of statements by context is extremely relevant for several reasons, among which we highlight. First, statements which students are already familiar with can help in the process of engagement and learning. Second, students will find it easier to understand the relevance of programming in their professional lives. Third, teachers can use this automatization to generate personalized lists. And fourth, students could use this automatization to select problems to which they are used to, facilitating their process of learning a certain programming topic. In closing, the first step was taken to generate personalized program lists according to the context of the undergraduate course. Thus, as future work, we intended to further evaluate the effect of the personalized programming problem assignments using our method to detect the subject matter. Thus, we can explore if the performance of the non-CS students will be affected when solving problems related to their courses. This research work was partially funded by Samsung Electronics of Amazonia LTDA within the scope of the project for education and research, SUPER. This is our references. And that's it. Thank you very much for hearing.